Welcome to Soil Structure Engineering Problems YouTube channel. So in this new video, I wanted to go and to explain, a little bit more the models, the linear elastic models, because as I mentioned in previous videos, it's important that when we set a model, we understand exactly what we are setting, and we understand exactly that the results that we are getting from this model depends on the decision we make during the pre-process. So in the pre-process, we define the type of materials we are going to use in terms of its mechanical behavior or thermal behavior or hydraulic behavior. I will focus in this case in the mechanical behavior. So on the first model we study when we do courses in civil engineering is the material model defined by the Hooke's law. So the Hooke's law is usually defined in one dimension only. So as you can see on the screen, when we say that a material is linear elastic, we are referring that a material that can be tested in the lab, for example, a bar of steel. And when we pull this bar, we are going to have a result, a relationship between the forces and the deformation of this bar that can be transformed to the stresses, the axial stresses, dividing the force by the area of the bar, and we can transform the displacement in strains, dividing the increments of the deformations over the original length of the bar. So in this way, we can have, for example, a curve, typically for ductile steel that you see on the screen, where you have the relationship between the stresses and strains of this material and their axial actions or axial stresses. So in general, we say, well, in this case, in the first part of the experiment, we can identify an area where we have a linear relationship between the stresses and strains. After certain limits, we are going to start having some sort of non-linearities, that there is a small region in here where you will find that the material is still elastic but non-linear. And after that, you will have a phase of plastic behavior that is not what we are interested in this particular video. So we are going to stop the analysis in here in the yield limit for axial stresses. So we are going to consider that our material will behave linearly exclusively. So when we do this study in one dimension, so using basically the axial test, we can express the relation between these stresses and strain by using the quantity E, which is the Young modulus, and is in this graph the slope of this straight line in here, as you probably know perfectly well at this stage. So this expression is limited because it's an expression in one dimension, and the problems we face in engineering are all of them three-dimensionals. So we need to, in order to use this theory of linear elasticity, we need to extend these principles to the three-dimensional space, basically. So when we go to the three-dimensional space, what we have to understand is that we have to define a few new entities, and we need to use more powerful mathematical tools to express the relationship between stresses and strains. And this is the reason why in the first place we say that in the three-dimensional space we study a small or infinitesimal cube. For example, this cube in this refer to this coordinate system x1, x2, and x3, where you have axial stresses acting on these faces and you have shear stresses acting on these faces. The reason why I'm using the axis x1, x2, and x3 instead of x, y, and z is simply because I will use something called the indicial notation, and it's more convenient for me to use this nomenclature to define the entities we are going to use in this explanation. So in the first place, considering these three axes or orthogonal axis in the three-dimensional space and this infinitesimal cube that represent a point on a soil mass, for example, or a point in an structure, allowed us to define what we know as a stress tensor. A tensor mathematically is an entity that is, let's say, more powerful than a vector because it had more components, so we can do more things with this entity. And for example, we can define the state of stresses at a point of a solid. This tensor stress is sigma with subindexes I and j, because and this y and j can take the values 1, 2, and 3, so the three directions of the space. And in this way you can define 9 components, the 9 components of the stress tensor that you can see on the figure in the coordinate system and in this small cube. So this is an alternative way of expressing the stress tensor, but it's exactly the same as when you use the axis x, y, and z. So it's just much more convenient because I'm using this initial notation in here. So once you have stresses or loads on a solid, of course you will produce deformation, and we say that, or we tend to analyze this in components. So this is the reason why if you start analyzing plane by plane what happened in the 3 dimension, you will find that the axial stresses will produce axial deformations, and the shear stresses will produce shear deformation or distortions. And this is what we express all together in the strain tensor I have in here. That is epsilon ij, same concept as the stress tensor. So we have 9 components because it's a second order tensor, we say, because it has 9 components, is 3 dimension of the space a square. This is the reason why you have 9 components. The diagonal of this matrix in here that we use to represent the tensor are the axial deformations, and the others are the distortions. So with these 2 entities, mathematical entities, we have a complete description of the stresses in the 3-dimensional space and the complete description of the deformations in the 3-dimensional space. Of course, the axial deformations and the distortions are related with the displacements when we talk about deformations, and these tensors are not expressing directly the deformation, but the strains, the axial strains and the distortions in our material, as you have studied before in elasticity. So the generalization of the Hooke law, that is in 1 dimension sigma equal to E times epsilon, is going to be the stress tensor is equal to the strain tensor multiplied by another tensor that is a more sophisticated or of a higher order tensor. Is a 4-order tensor that is called the stiffness matrix when you express this as a matrix, or the stiffness tensor when you express as a tensor. So in this case, we are using initial notation where this is the stress tensor, this is the stiffness tensor, and this is the strain tensor. So in this way, we can generalize the concept of Hooke's law in the 3-dimensional space to study what is exactly a linear elastic model. So when you expand the initial notation in here as a matrix, in a matrix form, you can transform the matrix that represents the stress tensor in a vector of 9 components. The matrix that represents the strain can be transformed in a vector of 9 components, as you see on the screen, and the stiffness tensor will become a stiffness matrix with 81 components. So the most general expression of relationship between the stresses and strains in the dimensional space demand from you to have a stiffness matrix with 81 components or 81 values to be defined and to define this elastic relationship between the stresses and strains. So this could be very, very general mathematically, but we are going to see how to simplify this expression in order to have less parameters to define when we define a material behavior in our models. So, for example, the fact that, as you know, you probably know that the stress tensor and the strain tensor are symmetric. So, for example, let me just clarify what is this. So, in this stress tensor, this means that this component sigma 2 1 is equal to sigma 1 2. This component sigma 3 1 is equal to sigma 1 3, etc. and etc. So, all the elements regarding the main diagonal of this tensor are symmetric, and the same thing happened with the strains. So these facts make our life easier in the sense that you can reduce the components you have to deal with for the stress tensor to 6 because of symmetry, and to 6 components for the strain tensor for the same reason of symmetry. And this will produce as well something that is called symmetries in the stiffness tensor, are minor symmetries that will reduce the number of elastic parameters needed for this relation to 6 times 6 is 36 constant, only in comparison with the 81 originally we have is much less, number of elastic properties. But this is still very, very general because this is taking into consideration only the symmetry of the stress tensor and the strain tensor. So in this case, as I said, you can express as well, instead of expressing this twice, this value here, something that's more familiar for us engineers is the distortion directly, as we used to study them in 2 dimensions. So in this case, we have 36 elastic parameters to be defined, so a lot of them yet, so probably we need more simplifications to tackle problems in engineering. The thing is that it can be demonstrated that this stiffness tensor is as well symmetric, and this is very, very convenient for us. This is this fact, and there are real materials that follow these properties. Reduce the number of elastic parameters to 21 because there is this symmetry between the blue components of this tensor and the red component of this tensor. So these parameters are the same, so symmetric. The matrix is symmetric and the tensor is symmetric as well, and we reduce the number of elastic properties to 21. When we have as well, apart from the symmetry of this stiffness tensor, we have as well symmetry in properties regarding planes, and this is a particular case where the symmetry is produced regarding the 3 coordinated planes. So we can find that many of the parameters of this stiffness tensor are equal to 0. So for something that we call an orthotropic material, that have different behavior in 3 perpendicular directions, typically related with reality with geomaterials. So it's going to be very useful for us. What happened is that we reduce the number of elastic parameters, independent elastic parameters, from 21 to 9 parameters only. So this allowed us to simplify considerably the material model in our simulations. So continuing with the simplifications, as you know, we have used before the isotropic materials, and the isotropic material is a particular material. For example, the steel is something quite isotropic, so we can say that the steel is isotropic, and the metals in general are isotropic. They are isotropic, and we need only 2 independent parameters to define the behavior or the relationship between the stresses and strains. And this is the shape of the stiffness matrix in terms of the Lamé constant, lambda and mu. But these 2 elastic parameters could be several pairs, because we have several elastic parameters defined in different ways depending on the problem. For example, in here you have the same isotropic material expresses in terms of the bulk modulus and the shear modulus that you can define as well as your model. So in any case, independently of the modulus, elastic module you use, the important thing to know about the isotropic materials is that they need only 2 independent elastic parameters to be defined. And this is what we did basically in previous videos in ANSYS Workbench. So what I'm going to do now is to show you in ANSYS Workbench how we can set up very easily an orthotropic material, which is a more complex material and a more realistic approach when we deal with geomaterials like soils, for example. So we have been using the isotropic material only defining the Young modulus and the Poisson ratio. So with a similar, expression to express the relationship between the stresses and strain. But now what we're going to do is we're going to show how to define an orthotropic material, which is a material that needs 9 elastic parameters to deal with material that have not the same elastic behavior in every direction, but have, different behaviors in 3 different perpendicular directions in the 3-dimensional space. So going back to our model in ANSYS Workbench, so we have this group of 9 piles interacting with 2 layers of soils. I will show how to set up an orthotropic model in a very simple way. Actually, in here, for example, I have set already the same model we did linear, elastic, and isotropic as an orthotropic for 1 layer of soils. So what I did was to create another engineering data to define the orthotropic materials. And if we double click in that one, you can see that the soil 1 is already, in this case, defined as an orthotropic elasticity instead of isotropic elasticity. So you find this option in here. So if you double click in orthotropic elasticity, you will open these new options in here, and you have to fill with the elastic parameters that are in this case defined as the Young modulus in the x direction, in the y direction, and in the z direction, the Poisson ratio in xy, yz, and xz, and the shear modulus in xy, yz, and xz. And these are the values I have defined in this case. I took the opportunity to define as well another thing that is orthotropic and possible to be defined in the software. So you can define as well the orthotropic stress limits. So these are a sort of yield strengths in every direction. So the tensile yield strength in the x, y, and z direction, the compressive in the same directions, and the shear strength as well in the 3 directions possible in the 3-dimensional space. So, in order to show you in more detail how to do it, I will go to the second soil we have in this problem, and I will show you that I have this definition of the isotropic elasticity in here and the tensile yield strength and compressive yield strength. But if you want to improve or you want to change it to orthotropic, you just double click in orthotropic elasticity, and you have in here to define the values of these parameters in the 3 direction of the 3-dimensional space. So I will change all of these to megapascals because I prefer to use these units for the elastic parameters. And for example, if in my isotropic elasticity I have 50 megapascals as an isotropic Young modulus, I will say that in the z direction I will keep this value, and I will use reduced values in x and y. Let's say that I know I have information from the lab that this is the case, or from the field for my soil, and the shear modulus will be usually less than this. Let's say it's 15 in every direction. So you don't need to use different values in every single direction, because sometimes what happens is that the material is not mathematically orthotropic but have different properties in the vertical and axial direction. For example, you can say that this is 20 and this is 20 in the vertical directions, and this is 15 in the x direction. The Poisson ratio can be different as well in every direction, or can be the same in the 3 directions. I will choose to use 0.25 for this direction and 0.2 in the other 2. So defining the values for the elastic parameter, you have defined a material which is orthotropic elastic now, and I can keep the as a definition of the strain these two values only, or I can go for the orthotropic as well if I want. So in order to do that, I just need to double click in orthotropic stress limits, and you can set as well orthotropic strain limits if you need it. So the options are up to you and depend on the needs you have for your model. So once I have changed the values for these parameters, I will refresh the model and I will update to recalculate everything, and we are going to see if this work or not, because sometimes the problem is when you start defining more complex models, you find yourselves in a problem because the change in the parameters has produced the failure or no convergence of your simulations, for example. So I will click in update for the model to recalculate for this structural analysis with orthotropic materials with the same restrictions, loads, and connection we have defined for previous problems. So we see the setup was successful. Now the solution is being calculated. So we are going to wait for a while for having the results. You can see the progress of the calculations in here. So I have some issues with the license apparently. That is resolved now. Still having some problem with the licenses apparently. The process. Apparently the calculations are being done. Okay, I managed to end the simulation for this orthotropic material, so I can show you now that everything was okay with the parameters we had set, so you can try by yourself in your software directly. So basically I'm just showing in here some results to see that the results were successful with the orthotropic material. So setting up an orthotropic material is very simple in ANSYS Workbench. You can get results of most sophisticated models considering materials, orthotropic materials, like for example reinforced concrete or for example soils. And this is still a model that is linear elastic, but it's not isotropic anymore, it's orthotropic. So it's a little bit more complex, it's a little bit more realistic, let's say. So a possibility to take into consideration when you set the relationship between the stresses and strains, and when you set as well, as you saw, the stresses limits, for example, the strengths in the three directions of the three-dimensional space. Thank you for watching.